Okay, so before we get into this problem 4 on the week 8 in-class examples, um, I need to talk to you a little bit about the periodic table. So with the periodic table, we can go in and we can divide the periodic table up for these purposes into 4 groups. So these first 2 columns, this middle group of 10 columns, these last 6 columns, and then those guys down there at the bottom. Okay, once we've done that, I can go and put some labels on these. So these, well, one other thing I want to do is, for this purpose, helium is actually better served right here. It's best for us to imagine that helium is right here for the purposes of doing electron configurations. And then we can call these first 2 columns the S block. These guys here in the middle, the D block. The ones over here, the P block. And those down here at the bottom, the F block. Even more than that, I can add a little bit more information. So I can go down through here and label N values. N equals 1, 2, 3, 4, 5, 6, 7. This is the NS block. Okay, and over here on the right-hand side, this is the NP block. So these guys right here are the 2p electrons. Okay, and 3, and 4, and 5, and 6. The other ones get a little bit weird. So this is the N-1 D block. So, for example, vanadium, the electrons of vanadium are 4-1. These are the 3D. This block here at the bottom, this is the 3D block of the periodic table. So this whole row is 3D, 4D, 5D, 6D that we have there. Okay, 3D, 4D, 5D, 6D. And then those at the very bottom end up being the N-2 F block. And this F block, if we had the arrangement of the periodic table where really this has gotten cut out, you should notice it's cut out of right here. And so that makes those be the 4F and the 5F, because their proper N values are 6 and 7. So 6 minus 2 is 4, 7 minus 2 is 5. All right, with that in hand, we should be able to now rapidly do some of these electron configurations. So what we do is we start at hydrogen and basically grow until we get to whatever our atom of interest is. So our atom of interest in this first one is lithium. And so I start at hydrogen, and to get to lithium, I have to go 2 steps into the 1s block. So that's 1s2. I have to step twice through the 1s block. And then I take a single step into the 2s block, 2s1. 1s2, 2s1. I'm going to go down and do these, and then I'm going to do the middle column later. So I'll do the electron configurations, and then we'll move to the valence the line diagrams, and then we'll finally go say whether they're diamagnetic or paramagnetic. All right, so next is beryllium. Beryllium, again, I start at hydrogen. I have to go 1-2 steps through the 1s block, and then 2 steps through the 2s block. So beryllium's electron configuration is 1s2, 2s2. I'm going to skip over a little bit on the periodic table. Start again at hydrogen. We go 1s2, then we have to go through the 2s block, 2s2, and then I need to take 2 steps into the 2p block. So 2p2. All right, going to jump over another element or two. So oxygen. Again, going to start back at hydrogen, 1s2, take 2 steps through the 2s block, 2s2. I'm going to take 1, 2, 3, 4 steps into the 2p block, 2p4. All right, now I'm going to go a long ways, or a lot further. I'm going to have to count all the way over here to argon. Okay, so I'm going to go 1s2, 2s2. Now I'm going to have to go all the way through the 2p block, 2p6. That's 1, 2, 3, 4, 5, 6 steps. That puts me right here. I got to go through the 3s, 1, 2, and then I got to take 1, 2, 3, 4, 5, 6 steps in the 3p. 3p, 3p6. I'm going to go a little bit further. Go faster with this one because it's should start to see the analogy now. Okay, so I've got to get all the way to potassium. So I'm going to take flip-flop this maybe. All right, now we're going to go all the way to potassium. Okay, and so to get to potassium, just like every other time, we start here with hydrogen and we go 1s2. Then I need to take 2 steps through the 2s block, 2s2. And I need to take 6 steps through the 2p block, 2p6. I'm over here now. I need to take 2 steps, 3s2. 6 steps to get through the p block, 3p6, and then a single step into the 4s block, 4s1. All right. Calcium's right next door, so let's run through this one fast. 1s2, 2s2, 2p6, 3s2, 3p6, and now I need to take 2 steps into the 4s2. All right, now it gets harder the bigger the numbers get. So now I'll talk about titanium, which is 22. It gets more interesting here too. So we do 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Remember again, this is the 3D. So this is something strange happening here, 3d1. It looks weird, but we're doing the right thing because we go from 4s to 3D. Here we always went 1s and then 2s and then 3s. Well, here we went 1s and 2s and 3s and 4, and then we're into 3s again, so it feels a little bit weird. Well, this is a point that I introduced now. So if we look up here at argon, we have something that's called noble gas, a noble gas configuration. And that's nice for doing these transition metals, the D block elements, because this whole chunk is the argon core, and that's this whole piece of titanium. And what that allows us to do is to write argon in square brackets, 4s2, 3d1. Okay, saves us a whole bunch of time. We just go back to the nearest noble gas, write it in brackets, and then from there write what's outside of it. What's outside of the argon core is 4s2, 3d, 3d2. Okay, so Now let's go over one more element. So look at vanadium. Okay, so vanadium is next door to titanium, so it's going to be the same core, argon, 4s2, 3d. Okay, we're 3 steps into the D block. 1, 2, 3 to get to vanadium. So it's D3. All right, go to chromium. Chromium has an argon core also. 4s2, 3d4. Well, that's what I want to write, but that's actually not true. So chromium and copper are exceptions. And it ends up, for some pretty complicated reasons, that in this electron configuration for chromium, I'll write it over here, that it's argon 4s1, 3d5. So it ends up that these transition metals atoms are particularly happy when they have a half full, and we'll see here in a second, or a completely full D shell. And this makes the D half full. Okay, it's got spots for 10 electrons. If we put 5, that's exactly half. And so an electron hops from the 4s over to the 3d. So the one that I'm Xing out is not the correct electron configuration. It's the one here. So copper is 4s1, 3d10 for similar reasons. Okay, the completely filled D is also an energetically favorable state, and so an electron jumps from the 4s over to the 3d. Iron here now has a regular electron configuration, argon 4s2, 3d6. But I've added a couple of ions of iron here. So iron, if we lose 2 electrons, this is very critical that we lose the correct electrons. We always lose electrons from the highest principal quantum number. So check this out. Argon 3d6. So it is those 4s electrons that disappear. But then if we need to remove an additional electron, okay, so if I've removed 2 from there, but I need to remove 3, now I can start to remove the d electrons. So I needed to remove 2 electrons to go here, and 3 electrons to go there. All right, let's now go to the middle of this now. And we'll work these 2 columns kind of hand in hand as we do. So 1s, 2s. Okay, and we need to see if we have unpaired electrons at the end of this. So these 2 electrons are paired, however, there's no pair for the 2s. So there's only an up electron, no down electron. If we have 1 or more unpaired electrons, it's paramagnetic. All right, beryllium, 1s, 2s. My 4 electrons go 1, 2, 3, 4. I have 2 up and 2 down electrons, so that's diamagnetic. All right, here with carbon. So you'll see with this one why I need to sketch out the levels. Because you might go, oh, well, there's 2 and they're paired, and there's 2 and they're paired like this. Well, then the other 2 are paired. But check this out. Not according to our rules, they're not. So 1, 2, 3, 4. Remember, our rule here is that we have to go all ups before we put any down electrons. Because this is more energetically stable to have the 2 electrons up in the atom. Well, 2 electrons up means it has 2 unpaired electrons, and so it is paramagnetic. All right, oxygen. Again, we do not know until we've sketched the boxes because it has an even number, so maybe they're all paired. But let's see what it does. 1, 2, 3, 4, 5, 6, 7. Okay, we got 7. That means we have 1 more electron to assign, 8. Well, we also, for this one, have 2 unpaired electrons, those 2 up electrons, so this one's also paramagnetic. Argon. All right, something like that. Messing my line up. So we have 2, 4, 10, 18 electrons to assign. So 1, 2, 3, 4, 5. Oh, I didn't get myself enough lines. Okay, 2, 4, 6, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, that's kind of ugly, but so we have all the electrons all paired up, so argon is diamagnetic. Let me write that at the top here a little bit cleaner. Okay, 18 electrons all paired, so the argon is diamagnetic. All right, now if we go in and put our 19 electrons in for potassium, okay, and that 19th electron is up with no paired down electron, so that's paramagnetic. Okay, I got my levels here for calcium, so the bottom is all the same. And now one up and one down for the 19th and 20th electron. So this one is diamagnetic. All right, hopefully you see by looking that always the core electron groups are all paired up. So even when we got something like, I'll show my better version of the argon configuration here. So if there's a chance for something being unpaired, it's in those outer layers. And so that makes it easy for us to do our transition metals because we don't have to consider this entire argon core. We really only have to consider the 4s and the 3D levels, what happens in them, because all that lower stuff is all paired up. All those core orbitals are all paired up. And so what I have to do is put my electrons in just to the valence orbitals. And so I got 2 electrons in the D levels. And so this is the same. This is paramagnetic. Okay, here again with this one, it is paramagnetic because all the lower stuff's all paired up. I have 3 up electrons, no corresponding down electrons, so that makes that be paramagnetic. Here's chromium. Okay, chromium has an up electron in the 4s, and it has 1, 2, 3, 4, 5. Okay, so this has 6 unpaired electrons, so this is paramagnetic. Copper. Okay, 4s1, 3d10. It's kind of an odd duck because the 3D's all paired up, but you got an unpaired electron in the 4s. And so an unpaired electron anywhere makes it paramagnetic. Here's iron. Okay, there's iron 0. I've got 4 unpaired electrons, so it's most definitely paramagnetic. For my iron 2, this now is empty. 4s is empty. And I have 1, 2, 3, 4, 5, 6 electrons in a 3D. So I have 4 unpaired electrons, so it also is most definitely para. And iron 3 is going to be the same situation. So 1, 2, 3, 4, 5. 4s is empty. It was oxidized away. I have 5 unpaired electrons in the iron 3, so para.